see. Okay. Are there any questions temporarily before we start back again? Oh, there are some questions here. One unique difference between NAM and ARM, for example, if possible. I one of the questions that was asked is an example between NAM and ARM. But I don't want to divert right now into that. I just introduced that as a to whet your appetite. There's a lot more work on that, and the best place to look at would be the paper in IEEE transactional reliability that I mentioned with Mansharamani and Nambiar. But also, the specific examples are given in the papers with people with Napoli that we published about Linux and MySQL. There is also ISSRE 2013 paper with this the model bugs that were there originally were removed and then were inserted back, and a lot of studies done on that one. So I would rather Manpreet's question on examples of non-aging related model bugs and aging related bugs is deferred to the papers rather than mine discussing here right now. Okay, back to where we were. Let's see. Okay. So we want to do the availability analysis of. So this particular paper, Trotki, Kim, Mansharamani, Nambiar, Matera, Trivedi, that paper has concrete examples of Mendel bugs and aging-related bugs. And this paper is primarily devoted to NAMs, non-aging-related Mendel bugs. And of course, there is a whole book on software aging and rejuvenation, a handbook. So that gives a lot of information in aging-related bugs. So I would not get more into that in this tutorial right now. So anyway, back to the availability model of this SIP on WebSphere. So I asked them, first of all, there were 112 components I had counted, hardware and software, for this system. So if you were to do, if each component has only 2 states, up or down, which it is not, then the number of states will be 2 to the power 112. So I don't want to do that, or you don't want to do that, right? So I started by asking them, tell me what all things can fail. And on one side, I put the hardware failures, and on the other side, I put the software failures. Hardware failure wise, power subsystem, cooling subsystem, blade, mid-plane, network, etc. And blade has many different subsystems. On the software side, there is operating system, and application wise, we have WebSphere application server and proxy server here. And it turned out that we had already done the blade center availability model by the time we went on to the SIP. So our major task was to worry about the software part. Hardware part was already done. So Single monolithic Markov model will have extraordinarily large number of states. So we use a multi-level approach, as was indicated earlier. So subsystems are modeled using Markov chains to capture dependence within, and fault tree used at the higher levels, as independence across subsystems can be reasonably assumed. And actually later we will see that there was a dependence across subsystems that we will resolve in a way. So this is an example of hierarchical composition. A single monolithic model is not constructed, stored, or solved. Each submodel is built and solved separately, and results are propagated up to the higher level model. And our software package SHARP facilitates such hierarchical model composition. And so let me give you the top level model. Top level model we used was a fault tree. Remember that there are two pieces of software from the application's perspective. One is the proxy and the other is the app server. And remember that there are two proxies, and one proxy will be enough for system to be functioning properly. So, and since there are two proxies, they are in parallel redundancy, and fault tree says AND gate for parallel redundancy. So this proxy and that proxy both have to fail for system to fail. Now, proxy fails if the proxy software fails, or a blade server on which this proxy is allocated fails, or the chassis common area like power and cooling, etc., on which this blade server is located fails. So that's why there is an OR gate. This fails, or this fails, or that fails. Notice also that chassis common for CM1 on which other blade servers on which application servers are located are here. So this is a repeated node, repeated event. All of them are submodels though. So anyway, it's very easy to see why this portion of the fault tree. Similarly here, there are 12 app servers, and we are making it more general rather than simply 7 out of 12. 7 of 12 meaning if seven app servers fail, then system fails, because 6 are necessary for system to work properly. But I have just made it K so that I can play with that K. Okay, so now at the lower level, at the middle level, I have the chassis common. Chassis common has 3 parts: plane, cooling subsystem, and power subsystem. Blade server itself has so many different subsystems. And then I start developing the Markov models of the individual component or subsystem. This is the mid-plane Markov model. This is cooling subsystem Markov model. And once again, they are not given to me. I have to ask them questions, loaded questions. What happens after this thing fails? Is there detection? Is there recovery? What kind of recovery? Is there probability of no recovery? Is it, etc.? Is there a delay involved in this, and so on? So by repeated questioning, I derive these models. And so one after the other, and I have shown you some models already. I have shown you this operating system model that we use. And I've also shown you the app server model, which is also the model for proxy that we use. So overall model then can be seen as a hierarchy like this. And of course, I have not shown everything yet. There's a lot more. So it's a fairly complex subsystem. And first is developing the model after having discussed everything and learning everything from the designers and users and so on. And then, in order to solve the model, to define an answer of system availability, I need parameters, input parameters. And what kinds of parameters? So parameters can be hardware component failure rates, software component failure rates, and after failure there might be detection, restart, reboot, and repair. And all of these may have delays attached to them, as well as probability of functioning correctly. Each detection may or may not work correctly, so there is a probability for each of these. So I need 4 types of parameters. Now, some of these parameter values might be available directly. Some may have to be experimented with, and some were not available even after all the effort. So, hardware component failure rates, every company I go to, they always have some data available from the previous field data or experimental data or whatever. So every hardware component, they will give you very reliable failure rate or mean time to failure. To find the detection, restart, reboot delays, it turned out that before I was given this modeling task, another group in IBM Annapolis lab was already injecting faults into this SIP implementation on WebSphere and had obtained data that was useful for us to estimate the mean detection delay, mean restart delay, mean reboot delay, and so on. But these two coverages, in most companies I've dealt with, there is no information on coverage. You simply assume 9.9 and then you vary over a range to see the effect of the assumption. But the most surprising thing was that there was no information available on the three pieces of software failure rates. What are the three? Proxy, SIP proxy, app server, and Linux. Repeated questioning all over the company did not reveal any data. So we simply assumed something in our models. So based on what I proposed, IBM and the customer agreed on those three values. Clearly, there is a lot of uncertainty in parameter values, particularly when you are assumed, but also when it is based on field data, because it will have always be in limited test data. So sensitivity with respect to these parameters need to be performed. Anyway, just to give you the realism here, these are the set of parameters, and these are not the real values, but each parameter in the model was given a value, and then we solve the model, and we find, we vary k. Remember, k is the number of components, and we not only compute. Hello, is there a question? There's some noise there. Okay, we not only compute the overall system downtime, but also downtime by each subsystem, operating system, hardware, proxy, app server, and total downtime, and so on. And then they will say, but what if we want to improve this because this is not good enough? Then we will tell them this is the one you try first, because that is the largest contributor to downtime and so on. So so what we developed was a very comprehensive availability model in which hardware and software detection delays were included, software failover delay was included, escalated levels of recovery was included, imperfect coverage was included, and many of the parameters collected from experiments, some obtained from tables, and few of them assumed, and detailed sensitivity analysis to find bottlenecks and give feedback to the designers. And we developed a new method of calculating DPM, defects per million, taking into account the interaction between call flow and failure recovery and retry of messages. And this is published now. This is an old slide. This model will be published in the future. And this model was responsible, I was told, for the sale of the system by IBM to the customer. And you can see the import graph in this case, based on what we discussed so far. Okay, so hierarchical composition. Many more examples of such models can be found in the Green Book. They, for availability models, for reliability models, for performance models, for performability models, for survivability models, for dynamic fault-free models, and so on. So last 3 chapters are full of this multi-level hierarchical composition and so on. But hierarchical composition, there are many questions with respect to it. Now, it starts with decomposing first. So should you decompose at the matrix level, at the model level, or at the system level? There's a lot of work done earlier on matrix level decomposition by P.J. Kotua and so on. My problem is that in real practical situation, generating the state space or the matrix of the underlying stochastic process is next to impossible. So we should be either doing model level decomposition or system level decomposition. System level decomposition is almost always available because we have subsystems that are given to us. But model level decomposition is also possible if you have a higher level model formalism that such as stochastic reward net, then you can form the overall system monolithic model using models, but then you can decompose that model, stochastic reward net model. Multi-level modeling formalism. I don't believe that formalism exists, and we need to develop, and we have some effort, little bit of effort, develop meta-modeling language. And then what kinds of quantities to pass between submodels? Is there a restriction or is it arbitrary? Is the solution that we obtain by this hierarchical composition exact or approximate? If it is approximate, can you bound the modeling errors of approximation? Can you estimate or bound the errors? And the import graph, is it acyclic or has cycles in it? If the import graph is acyclic, then we can continue with the hierarchical composition. But if import graph is cycles, then hierarchical composition doesn't work, and we need to evolve to the next stage, which is called fixed point iteration. So we have now covered the first three: the non-state space models for efficiency and simplicity, state space models for dependency capture, hierarchical models for largeness avoidance. But sometimes hierarchy is not enough. We need to do fixed point iteration. So there are two examples of fixed point iteration I have here. The first one I'm going to browse through, not go through details. Second one I'm going to take a little bit more time. But many more. There's a whole chapter on fixed point iteration in the new book. So where does fixed point iteration arise in our SIP model? Let me briefly tell you. We ignored one dependence, assuming that its effect is negligible. And this dependence, let me show you where. Remember that two app servers share a single blade server node. Two WebSphere application servers are located on a single blade server node. And so you see this, that AS1 and AS2 are on the same blade server node. So why does this independence? Well, multiple things. Two app servers share a blade server node. If one app server needs reboot its operating system or repair of the blade is needed, it affects the other app server on the same blade. This is a forced dependence. We ignored this dependence earlier, and to account for this dependence, what do we need to do? So these are the two Markov models of the two app servers that we have used so far. Now, suppose that in this particular Markov model for one of the app server, the reboot is not, the reboot is required. If reboot is required, that means the whole node is rebooted. This is pre-VM days. And that means this guy will be also forced into a reboot. It doesn't want to, but it will be forced to. Similarly, if the repair is needed, then this guy is also forced into repair because the same blade. So to reflect that, these two Markov chains are not independent, but they are nearly independent. And so we need to synchronize these two Markov chains at state UB and at state RE. So we need to combine these two CTMCs. Now, combined CTMC will be rather difficult to construct by hand. So I resort to the formalism that I already mentioned, namely stochastic reward nets. And stochastic reward net can be then automatically converted to underlying Markov chain or Markov reward model to compute the measures of interest. So what I want to show you very briefly, and I'm not going to go through details here, and we start by converting first single app server CTMC into a stochastic reward net. By the way, this part is not published anywhere. It's not even in the book. This is only, I came up with it for this tutorial for you guys. So don't run and publish it without me, all right? So this is a trivially transformed Markov chain into the stochastic reward net, or stochastic Petri net, for a single app server. And then we use this as, just to verify, we use this SRN model to generate the Markov chain and check whether we got the same as before. And now we combine these corresponding to SRNs into a single one. And this is what I come up with. So even this simple model in which two synchronized Markov chains represented as a stochastic reward net, and the dotted arcs represent variable cardinality arcs as is allowed in the stochastic reward nets. So if you were to use GSPN, this will be much more complex than the one I have used here. And then this can be converted into a Markov chain automatically. And we found that the underlying reachability graph has 65 vanishing markings and 66 tangible markings. So the underlying CTMC of the combined Markov chain of the two app servers together, sharing the blade server, has 66 states. And it makes sense to double check that if the two Markov chains are independent, the combined Markov chain will have 100 states, but there are 8 out of the 10 states of each CTMC are independent and 2 states are common. So it becomes 8 times 8 plus 2 is 66. And then after solving this combined Markov chain, I found the answer to the availability. But then I wanted to show that this can be done as a fixed point iteration problem. So I go back to the single Markov chain and I introduce extra transitions, which are the forced reboot of this app server due to the other app server co-resident on the same blade. And I don't want to go through the details, but this leads to a fixed point problem. And this was solved and compared with the combined Markov chain. And these are details of the fixed point left for you. And I found that the answers obtained by ignoring the dependence versus, by a single fixed point iteration versus combined Markov chain is not too different. And therefore, I could use the fixed point iteration in the overall system model. Okay, the second example I want to come back to for fixed point iteration is returning to our scalable model for cloud availability that we showed earlier, in which after 777, seven machines, physical machines in hot pool, 7 machines in the warm pool, and 7 machines in cold pool, I couldn't even generate the Markov chain or store the Markov chain. So now I take this model, stochastic reward model, and decompose into 3 submodels: one for the hot pool, one for warm pool, one for cold pool. And clearly, these 3 will interact, and interactions are introduced appropriately. And again, I can't go through the details. You have to go through the paper that I mentioned earlier in transactional cloud computing. And the import graph indicates here the interactions. So the probability P sub W is computed by the warm pool model and supplied as an input parameter to the hot pool model, and similarly other parameters. So notice that this particular import graph is cyclic. That means that I cannot solve one model until I solve all the others. So therefore, this can be cast as a fixed point problem. So in other words, I will break the chain here somewhere and assume a value for PW and PC, and therefore I can solve the hot pool model. Once I solve the hot pool model, I will be able to solve the other models and so on. I keep repeating this, iterating this until everything converges within a certain error. And it turns out that existence of fixed point is relatively easy. And there's a paper in 1996 that we wrote in a very general setting that shows the existence of fixed point. But uniqueness of fixed point, in some cases we can establish, but in general, it's a difficult problem. And the rate of convergence in general is a difficult problem, but in practice, we found that within 3 or 4 iterations, most problems usually converge. And what kind of accuracy you sacrifice and what kind of scalability you gain, all these are very interesting problems, and many theses are possible on these topics. So go through the Green Book and you'll find a lot of room for further thinking on how to propose more problems along these lines. And I have shown here in that particular problem of cloud that by using this fixed point iteration, we are able to solve 100, 100, 100 problem very easily. And I think we can go to 1,000, 1,000, 1,000 too. But you can see that you can extend the size of the problem way beyond trivial to something reasonable. So to summarize what we have done so far, steps for system availability or reliability modeling is list all possible component level failures, hardware, software, list all failure detectors and match with the failure types. You can go back and see each of these steps in the case of SIP application server. List all recovery mechanisms and match with the failure types. Allocations of software modules to hardware units. This was given to us in the SIP case, but there could also be something to be determined to optimize availability. Then you can formulate the model, and we can check with the people who know the system very well, explain to them the model you have come up with, and if they agree, then you've done phase validation. Then you have to parameterize the model, which some of the parameters may come from tables, some from websites, some from experiments, and then solve the model using one of the tools to detect bottleneck, sensitivity analysis, suggest parameters to be monitored more accurately, and so on, and what if analysis to suggest improvements, and so on. Conclusion. I believe that techniques and software packages are available for the construction and solution of reliability and availability models of real systems. System decomposition followed by hierarchical model composition is the typical approach. Modeling can be used and has been used to compare design alternatives at Cisco, find bottlenecks, answer what-if questions, design optimization, and conduct trade-off studies at certification time in Bobbio, for example, at design verification testing time at IBM in the SIP server. Configuration selection phase was used in digital equipment operation. Operational phase we are beginning to use more and more for software aging and rejuvenation. And the models type that are used, non-stage space models, reliability block diagram, fault trees, and reliability graph, stage space-wise Markov models and stochastic PPNets, but we can go to semi-Markovs, Markov regenerative and non-homogeneous Markov models if required. Hierarchical composition, top level usually RBD or fault tree. At the bottom level are usually Markov chains. But occasionally we have to do fixed point iteration. Solution types can be analytic closed form in some rare cases, but more generally analytic numeric using a software package, and occasionally we use simulation or hybrid. Software packages Sharp or similar tools are used to construct and solve such models. And structural as well as parametric assumptions means that numbers produced should be taken with a grain of salt. Challenges, model largeness in spite of hierarchy, fixed point iteration, and approximation, particularly when we go to smart grid-like situations. We started to work on that, but I ran out of good graduate students, so that work is hanging. There is a lot more possible if the smart people want to work with me. Dealing with non-exponential distributions in spite of SMP, MR, GP, NH, CPMC, and pH. Problem is not only computational, but also parametric. Where do you get the parameters for more complex distributions. Service-oriented measures as opposed to system-oriented measures. I mentioned DPM, that is defects per million among the telco. There are many others. Combining performance, power, and failure repair. This comes under the notion of performability, and a lot of work has been done, and that can be a separate tutorial on that topic itself. Model parameterization, it's an art, and model validation and verification, a lot more needs to be done. Some has been done. And parametric uncertainty propagation is a big topic in itself, and that is subject to another tutorial. I'm going to skip this one. Model parameterization we already covered, so I'm going to skip that one too. The message: pick a real problem rather than one from literature whenever possible. There should be plenty of real problems in industry. And keep an open mind. You're going to learn a lot about the system under consideration and possibly about the modeling methods. Ask questions and listen carefully. And it is possible to write scholarly articles based on work done on real problems. People often think that real problems means you are trying to earn money and not write articles, but that's not true. And use software packages, Sharp, SPMP, etc., whenever applicable, as opposed to writing your own code to generate and solve models. You are essentially wasting time because good tools are already available. And the book that contains all this material is divided into several parts. Introduction, chapters 1 through 3. Non-state space models, chapters 4 through 8. State space models with exponential distributions, chapters 9 through 12, part 3. And state space models with non-exponential distributions, part 4, chapters 13, 14, and 15. And part 5 is the multi-level models, chapter 16 and 17. And part 6 is the case studies, 18. Another way to look at what is done in that book is this particular chart. And there are many references on which I have picked this material. And emails, Andrea, Bobbio, and myself. And much of my stuff is available on the ResearchGate. I don't know, most of you are probably familiar with ResearchGate, where most of my papers are available. At this point, I will close and ask for questions, if there are any. I hope people are awake. They're all gone. So there are some questions, so let me see if I can go into backward. Is it possible to use the dotted arcs approach in Sharp? Does Sharp support S? Okay. Yes, dotted arcs in. Okay, which way do you want to go? Let's. Everybody can see these questions, right? I assume so.
Yes, Kishor, thank you.
Okay, so I'm taking this particular question right now. So first is dotted arc. Dotted arc I had shown was for a variable cardinality arc, and it is part of what is called stochastic reward net. So stochastic reward net is fully implemented at first in SPMP, my tool called SPMP, but it is also included in Sharp. So SRN is there in Sharp, and therefore by dotted arc is meant in that particular picture, variable cardinality arc is available in Sharp. Yes, that's answer to that question. Does Sharp support SMP or NH? Okay, Sharp supports SMP of a certain type, and it also supports MRGP of a certain type. For MRGP steady-state solution is accommodated in Sharp, where all distributions are expected to be what are called exponomial distributions, which are Coxian basically. Sharp doesn't support MRGP transient solution. Sharp supports SMP steady-state solution as well as SMP transient solution if SMP is acyclic. The SPNP supports Markov regenerative or higher stochastic weakness, but that it simulates, it does discrete event simulation, of FSPN and MRSPN in SPMP, the other tool that I have. Okay, so does that answer your question? Okay, please enumerate some sources to know more about current industrial real problems. I think, I don't know whether you'll find a lot more about industrial real problems in the computer and communication domain than what you find in the Green Book. You'll have to go through other domains like petroleum industry and so on, power systems and other sources. But computer and communication industry, I think Green Book is a very good source. Referring to largeness avoidance, hierarchical modeling techniques, why did you not apply it to Boeing example with 4 trillion paths? Yes, so very interesting. That's a reliability graph. And reliability graph, unless and until there is an intermediate node, I don't know how to do hierarchy there. Hierarchy is applied in a sense in there that each individual edge itself might be a subsystem. But given a reliability graph, the closest thing to hierarchy would be called conditioning or factoring, except you need to know what to factor on. And there is a considerable literature on finding out what to factor on. We didn't try that. It could be tried, I suppose. But if you know how to do hierarchy on that problem, show me how. It's very difficult. I don't see a way. Okay, thanks. One unique difference between NAM and okay, that I have answered. Any other questions? You can speak also if you like. Turn in your camera.
Yes, I have a question. Could you please explain the formula for the K out of N with non-identical components?
Yes, who is this?
I'm Marco Papini.
Yes, Marco. Okay, let me see if I can go back to that. Of course, this is explained in the Green Book, but let me explain to you.
It was the formula at slide
Hold
43.
on. I'm getting it. I haven't gotten it, except I forgot to share first. Okay. I need to remember to share it so that you can see it too, right? Okay, so the question is about this last formula here, right?
Yes.
Okay, so this is used in factoring. So suppose I have n components, right? So there are two. Let's consider the nth component. It's either up or down. So I'm factoring on nth component, right? So what is the probability the nth component is down? 1 minus Rn. What is the probability the nth component is up? Rn, okay?
Yes.
And now, if the nth component is down, then I need at least k out of remaining n minus 1. So,
Yes.
so that is why it is R k given n minus 1. If I find that the nth component is up, then I only need k minus 1 out of remaining n minus 1. That's why it's R given R k minus 1 out of n minus 1. So this is the use of what is called factoring, followed by the theorem of total probability, as you will find in chapter 1 of the Blue Book or chapter whichever 4 of the Green Book. So this recursive formula is obtained by simply doing the factoring or conditioning on nth component. And then since this is a recursive formula, I got to give you the end conditions. So one end condition that will be necessary is that looking for 0 components up out of n, you have probability 1, right? And looking for j greater than I components out of I is not possible. That's why 0. So given this, you are able to solve for any k out of n non-identical. All right?
Okay. Yeah. That's great. I think that from my point of view, the misleading information was that there was also PEDIX N, which is the nth component.
And given components.
Yes.
So what have you used?
In the reliability and the liability formula and the liability part, the n at PEDIX is the index of the component which has failed or which is working, not
Yes.
the number of total components in the system. Yes.
So the components reliability, individual reliability, R1, R2 to Rn, basically.
Yeah. Mm-hmm.
So I try to condense a lot of information into one slide. So I have too many slides is always my problem, you know. So fortunately, you guys were nice. You gave me 3 hours. Normally, people give me 1 hour or 2 hours, and I'm trying to condense the same information. It's a hopeless case, right?
That's quite interesting because I have always seen the non-identical case not using the recursive approach, but using the iterative approach to build it as a sum of sums of products.
So in my green book and the red book, the sharp book, I had given that formula, but this formula is now given in my second edition of the blue book as well as in the green book. Okay.
Okay. Thank you.
Any other questions? Feel free. Nobody is going to be. But is there any similarity between Sharp and Peppa? Okay, Peppa, I think Sharp is much older, and Peppa people used a lot of our papers to write the algorithms in their tool, I believe. So a lot of stochastic process algebra people joined the crowd a little bit later. And so I don't know more details, but I know that they have used, they reference our examples and our algorithms and so on. But it is certainly possible to turn Sharp and SPNP into model checking tools very easily if I had the energy and the people around me. I don't know what will be gained over Prism or Peppa, and I'm not sure. Any other questions? You're saturated? But you can ask me questions later, right? Is Ori's tool equivalent to any of the tools? I don't know Ori's tool. Where is it coming from? Tell me something more about Ori's tool, then I can tell you. O-R-I-S, Oris. I never heard of it. So, if there's a company tool, then company tools are more jazzy, more development on top rather than engines. Engines-wise, it will be very difficult to have something like Sharp. Such a multi paradigm. 5 nines and 4 nines. Okay. I have mentioned availability in the. Let's see where I can put that one. Skip that slide. Let me get to the right slide. So the question is explain 4 nines and 5 nines availability. Okay, yeah. So when, and they generally refer to steady state availability. When they say 4 nines, they want to say that steady state availability is 0.09999, 4 nines, followed by whatever, it may be 8 or 1 or 3, whatever. So 0.9999x, that is 4 nines. 0.99999x is 5 nines. So most technical companies want to claim 5 nines and 6 nines availability. So it's simply that steady state availability is claimed to be that many nines. Does that answer the question, or you need something more than that? Anything else? I enjoy doing these tutorials. I don't know how long I'll continue to do. I'm 74 years old right now, but I still have the energy to continue. So if you need me, let me know. Different to the largeness, okay. There's no other question. Andrea, you have any answers to anybody? Any message to anybody? Andrea, Bobbio?
I think that you can hear me. Yeah.
Yes.
Oristol is from the University of Firenze, from Enrico Vicario, you know?
Yeah.
But probably it's not very known around.
Okay, I should have known then. Yeah,
I don't know how this guy knows about Oristol, because it's not very diffused.
Okay. Yeah, so they're very good people. They're very, very good people. So I don't know what all they have implemented, but they've implemented recently compared with ours. So they could probably have. But to get to all the model types that are there in Sharp and all the hierarchy and fixed point iteration, I think it will be a long time before people catch up with that. And I don't know why they need to. If they can develop on top of Sharp, I would be very happy to help them do that. Not talking about Oris, I'm talking about generally. Sharp development started in 1982 and it still continues. So years and years and years of development and practical use. Anything else? Maybe it's time for lunch. Thank you very much. Namaste and keep safe. Namaste is good, instead of handshaking. These days we are not. And my culture provides you namaste.
Okay. So Kishor, really thanks a lot for organizing the tutorial. And also thank you to Andrea for creating the contact. And I want to also thank to Michela because she really helped me a lot in organizing all tutorials. So it was a very successful day. At the peak, we had more than 200 people connected. So it was a really, really nice day for the conference and our community. So really thanks a lot from my side, Kishor, and to all of also for attending up to this time, because it is your lunch time, it is our dinner time almost, and so thank you all, really.
Will you be able to send me the link to the recording? And how many total we had attended, we had in this tutorial? So I saw 65.
More than 100, and I think I will send you also all the emails of people who registered to the link that I sent. I put in the chat in the very beginning. And I'll keep in touch with the people, and I will send you the recording. I will put the recording tomorrow also available on the website in a way that people can also watch offline.
Okay, sounds good.
Thank you.
All right. Arrivederci.
Thank you. Thanks a lot. Thank you.
Thank you. Thank you all. Have a good time. Have a good night. Bye-bye.
Bye, Danilo.
Thank you.